Okay, our next speaker is Anton Pribytok from Trinity College, Dublin. Please, Anton.
Okay, thank you very much. Actually, today I'd like to represent part of the results which correspond to the papers from below. And essentially, this will be related to the potentially finding new deformations and novel models which could satisfy certain physical constraints. So let me recap some apparatus which would be relevant for this conversation. As we know, our setup starts from some quantum consistency integrability constraint, which is of course YB. But our final goal is relation to the holographic and, for example, integrable spin chains, which are coming in different AdS backgrounds. So for that reason, we need R-matrices, which are of so-called arbitrary spectral dependence. So essentially, they are not dependent on the spectral difference. Then another object which could be crucial for further algebraic conversation is the of course, you can construct your monodromy matrix and trace over auxiliary space. But for the moment, we can restrict all this to the regularity of the R matrix and the homogeneous limit of the nearest-neighbour interaction spin chain. And with that, as we know, there are two essentially crucial components which one would require is a set of conserved charges, and the first charge would correspond to the sum of the densities, and you can reproduce always your Hamiltonian from the spectral reduction from the R matrix, and of course the regular point should always exist there. And in principle, there are many ways how to proceed or construct a new model from the Yang-Baxter equation, but our approach will be based on different apparatus, which will involve certain automorphic symmetries. But the main point is that arbitrary or range R charge is of course follows from this differentiation, and your integrable commuting hierarchy is a set of commutators which must vanish, which is by default definition of the integrable system. So with this in mind, there are many ways like how one can construct new models from going to YB or taking the derivatives of the transfer and subsequently using RTT algebra. But instead, we want to try to use some automorphic symmetries, namely what is called the boost symmetries, and which the idea is straightforward that you can boost and lift your charges, build up the charges from the boost operator with some decreased range conserved charge. And in principle, it was known for the difference form, but we have proved and generalized this to the non-difference form to make a connection, as I mentioned, to the holography. And in principle, the whole conversation comes to the following equation, which we would need to solve. But the peculiarity is that essentially, in order to solve this, you end up with a first order nonlinear ODE coupled system, which requires a number of techniques to be used. But since we proceed in sort of inverse order as to what, in comparison to what people usually do, with having from this system identifying the Hamiltonian, we can solve build up from the expansion of the YB certain spectral points a differential system. Each of these equations would correspond to the reduction from the Sutherland equation. So you solve, and this is required to identify the associated R operator, R matrix. So with this in mind, you can build up the whole R space, but the problem would be that in principle, this space is too large and you need to use identifications, because essentially what we're interested is the different classes. So essentially, where we represent each class by a single generator. And this is, so eventually you can use normalization, reparameterization, local basis transform, and discrete transform, namely, I mean, that such combinations of the permutation and R matrix would again be solutions of YB. And you can twist, although there is a caveat about twists where you could apply or not. Because in principle, they could affect your spectrum and define different models. So in principle, basically, one can start with this straightforward ansatz in a certain basis. And the caveat is that at the level of solving this large nonlinear system, there will be some freedoms which will be associated to certain spectral functions and their associated primitives, which actually add freedoms to your newly found models. After doing all that, there is a way to find four interesting independent generators, essentially, and two of which, in our present understanding, correspond to the conventional difference form 6 and 8 vertex models. And the second pair corresponds to the 6 and 8 vertex type models, where your spectral dependence is manifestly of non-different form. And we were able to find that actually, as it is known, for example, in integrable models that correspond to the AdS2 and AdS3 background, consist R-matrix or S-matrix consists of 4x4 blocks, each of which individually satisfies the quantum constraint, quantum integrability constraint. And by the approach, it is sufficient actually to take the Hamiltonians of the associated string backgrounds and by identification through the spectral dependence of the Zhikovsky basis to relate them. And there are two distinct things that one is arriving at. First of all, the first is the AdS3 Hamiltonian could be related to the either 6 vertex B type, and this will lead to the continuous family of deformations, which are just in principle, which involve spectral shifts. This is one type of the freedom. And the second one is mapping to the 8 vertex B, but then this will be already with a single freedom of the elliptic deformation. And another part relates to the AdS2 sector, where you just have one freedom to deform the model, which exactly relates to this 8 vertex B. And just to mention that our newly found, especially this B sector, it satisfies what people call a physical constraint of free-fermion condition, which comes from this generalized algebraic equation, being this large kappa depending on it to be either vanishing or not. When it vanishes, it does satisfy the free-fermion condition. Just to illustrate that, for example, these 8 vertex, how do they look like, these A and B models? They involve a certain elliptic sector for the A class, but more interestingly, that this relation of the AdS2 and 3 models have an R-matrix, as again I mentioned, of this input, have this form, and where this these functions are of course certain elliptics and with certain gauged redefinitions with eta to be arbitrary functions on the spectral parameter and certain constant k's. Just to mention what a part of the message is that one is able to construct a non-difference form models by solving coupled nonlinear systems of the integrable hierarchy, which are following from your associated commutator. And after using identification variant symmetries, you are able to downgrade your large solution space to the generating solutions or just generators. And from these four independent models, we are able to extract 6 and 8 vertex type of two 6 and 8 vertex models of two different types, two of which are models and admit embedding, so that AdS2 and AdS3 spin chains become a special case of those models. And we also show that in principle, B-type models exhibit free-fermion symmetry, and we're also able to show, although I'm not showing this, that in principle one can derive also a deformed algebra. Also, particular form of it is still under investigation. And I want to raise a couple of questions that are related here, and which are still in progress. And the first one is, of course, what would be, is there a notion of the generalized flux, and if you want, amount control parameter of it. I'm also not showing SL2 sector, which is also having vast generalizations of, for example, Kulish model, which was found by them some time ago. And another point is that, for example, if it could have some interpretation in terms of latest works in deep brain embeddings. And also AdS5 sector has new properties and certain, if there is existence of the underlying algebras, quantum algebras. So yeah, thank you.
Okay, thank you very much. Let's thank Anton. And now we go to questions.
Yeah.
Sorry, just to clarify, maybe I missed that. So you have this ansatz for the Hamiltonian, and you found some particular parameters where this kind of local-looking Hamiltonian has integrability.
Corey, what do you mean? You mean like on these parameters, or?
So you start from this ansatz for the Hamiltonian.
Yeah, exactly. You have this ansatz. Okay, let me be maybe more clear. You have this ansatz. Okay, yeah, I haven't stated this explicitly. You take Q3, which is the next charge, and Q2, and you solve this coupled nonlinear system. The question is, of course,
wait, before that. So you have this Hamiltonian. Is it integrable no matter what or not?
Of course, this is a 8-vertex type, and just in some particular cases.
For any values of the parameters. Or you consider different cases after that?
Well, you eventually, this is...
You have 7 parameters. For any value of h's, it's integrable or not? What's the claim first?
No, in this form, you need to constrain it because, of course, it is of 8-vertex form, but you need to find how these h's are related and if they are related. And to constrain that, this is how you need to solve. You need to solve that, and from here you will be able to identify certain spectral functional relations on these h functions. Sorry, I think, yeah, that's what I'm saying here. Essentially, they're not just like in constant case. By constant, whenever you have R-matrix of this form, these h's are just constants. They are not spectrally dependent. And if you have...
What do you mean spectrally dependent?
There is no some spectral parameter dependence on them. They are not functions on some, in this case, function, I've not mentioned this function theta, which you need to...
But theta is what? Is a parameter for you?
Spectral parameter, yes.
No, well, if you just look at the Hamiltonian.
Yes.
H's are constants or not?
Here, no, that's the whole point. They are not constants. They are
functions of what?
Of spectral parameter.
But spectral parameter is like just additional notion you introduce to prove integrability. It doesn't have like physical immediate implications, no?
Yes, you have...
in the closed form, if you just look at the Hamiltonian, can you explain for what is the statement? If we don't mention integrability, I mean, if we just look at the Hamiltonian without our matrix.
Yes, integrability is constrained by this, you agree? But
so for which values of h's this model is integrable?
That's what you need to find for these values. For example, this is...
are they constant?
Is it a complete classification?
For this ansatz, for this R ansatz, like H, which is looking very similar, just it is complete. This is all 6 and 8 vertex types that you can get in principle.
And so only these 4 cases are integrable?
Sorry?
So only these 4 cases are integrable?
No, you can have, of course, one diagonal, which is 4 vertex or some 5 vertex, but we are not just considering them as an interesting one. And but getting back maybe to Nikolai's question is that sorry, I'm compactifying a lot of things actually behind, because of course eventually you end up with absolutely concrete expressions for these h's, which just show you a form of this operator, and for each of these h's, which is a Hamiltonian, you are building up another operator by solving another problem.
But okay, can you just give an example of H? Let's not go into too much detail. What is a Hamiltonian? So you claim certain Hamiltonian is integrable. Could you like show the more general form of it?
Yeah, you want to know how does Hamiltonians look like?
Yeah, because isn't it
yeah,
what we are trying to establish? But now we run out of time, so we should.
But maybe let me make a quick comment. Hamiltonians look with non-zero entries, for example, for 8 vertex like this 8 vertex R matrix, but with certain exponents and certain primitive functions of this form.
Now let's do the following. Now we have to go to the break, right?
Okay.
So maybe during the break, can you find explicit form of H's?
Okay.
Because for you, maybe H and R is immediately the same, and that actually requires some effort to decode. Right. So is the break now, Andrea?
Yes. So now we